All right, example 4.1.3, that will be the first example where we start looking at an inner product on a space that isn't Rn. So I'm going to take this space P3 of polynomials of degree 3 or less, and I'm going to define an inner product by evaluating the polynomials at -1, at 0, at 1, and at 4, and adding what I get. All right, so first thing I need to show is that this is an inner product space, and then I'm going to look at the length of a polynomial. All right, this should be a bit strange to you. We're looking at lengths of polynomials. We'll look at distances between polynomials. Soon we'll look at angles between polynomials, and that seems a bit arbitrary at first, but when we start looking at application, you could see why this is helpful, why this is useful, why even though it looks a bit arbitrary, it isn't in the end. All right, so let's look at example 4.1.3. I'm going to first show that it's an inner product. So I need to look at the 4 axioms and prove them. All right, so first I'm going to look at P of x, Q of x, and I want to compare it to the opposite. So this is P minus 1, Q minus 1, P0, Q0, plus P1, Q1, plus P4, Q4. These are all real numbers, so I can switch them. I'm multiplying real numbers here. So that would be QP. All right, axiom 2. I want to look at P plus Q R. I want to show that I can distribute the R. So this will be P minus 1 plus Q minus 1, R minus 1, plus P0 plus Q0, R0, plus P1 plus Q1, R1, and one more, so P4, sorry, it's a bit squish. Let me shrink it a bit up. Q4, R4. All right, now I'm going to distribute using the fact that the real numbers, so I get P minus 1, R minus 1, plus Q minus 1, R minus 1, plus P0, R0. There's no way I'm going to fit that one, so let me use a second line. All right, plus P4, R4, plus Q4, R4. All right, so what do I have? If I look at P, 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 those 4 together are going to give me PR, and then the remaining 4 are exactly what I need to get QR. All right, so nothing deep really, it's just using the similar property on real numbers. And same thing here, KPR, that's going to be KP minus 1, R minus 1. Let me put 3 dots just to save a bit of time. I think you're getting the point. And so I can take the K out. And so I get KPR. All right, final axiom. That's the one that's usually a bit more interesting. First, what happens if I do PP? That's going to be P of minus 1 times P of minus 1, P of 0 times P of 0, P of 1 times P of 1, and P of 4 times P of 4. That is definitely bigger than 0. And now this is the part that's interesting. So this is part 2. What does it mean that PP equals 0? So that would mean that P minus 1 is 0, P0 is 0, P1 is 0, and P4 is 0. So I have 4 different zeros, minus 1, 0, 1, and 4 for a polynomial of degree 3. But a polynomial of degree 3 usually has at most 3 zeros, right? X minus the first one, X minus the second one, X minus the third one when you factor it. That means if it has 4 zeros, it has everything 0. So P is the 0 polynomial. That's the only one that can have so many. All right, and that's part of the reason I needed to use 4 points here. If I use 3, then it wouldn't fit the last axiom. So it was a bit painful here, but didn't have a choice. All right, so yes, it is an inner product. All right, so now we want to compute the length of x squared plus 1. The first thing we need to do is to compute the dot product of x squared plus 1 with itself. All right, so I'm going to plug in minus 1 first, so minus 1 squared plus 1. I'm going to plug in 0. I'm going to plug in 1. And I'm going to plug in 4. I'm going to get 4 plus 1 plus 4 plus 17 squared. All right, 17 squared. Sorry, I actually forgot to square this. So it's 289. So that's 289 plus 9, 298. And so the length is the square root of that number. And that's root of 298. All right, so we can talk about lengths. We could talk about distances between polynomial as soon as you settled on a choice of an inner product.